Hello, my name is Eric Gillespie, and today myself, Nick Wagner, and Joe Hlebowski will be talking about electrospun fiber catalyst. Electrospinning is a process that uses an electrical charge to create a solid fiber from a liquid. The liquid, given a very precise set of properties ranging from molecular composition to viscosity, is projected from a syringe to a grounded plate. This fiber, depending on the composition, can be used for many applications. One application is using electrospun fiber as a catalyst. Now, many of the chemicals, even those that are electrospun, can be and have been used as catalysts in the past. However, one major advantage to using electrospun fibers is that they can be used for different catalytic purposes and often have higher effectiveness and longevity as catalyst. One such material that has numerous applications is electrospun fibers containing silver nitrate, or AgNO3. Again, this fiber over its natural form has higher longevity as a catalyst and higher effectiveness, which we'll talk about shortly. First, we have Nicholas Wagner discussing the structure of electrospun silver nitrate.
Hello, I'm Nicholas Wagner, and I'm here today to talk to you about electrospun fibers. More specifically, the type of catalyst used to make these electrospun fibers. The fiber we're going to be discussing today are silver nanoparticles, and it's both its application, its structure, and the way it's processed. The way that the silver nanoparticles is the way it's formed and made is kind of affects how the specific type of application it has and its properties. Now, it can either be made physically using a tube furnace or chemically using AgNO3 silver nitrate as a catalyst. The chemical method is much more common and widely used in the labs and so forth, and it's generally how it's made. And the way it's made is by adding different solutions to the silver nitrate, the AgNO3, and depending on the specific solution used, it will change the grain size, the number of grains per inch, or the reaction speed of the solution and AgNO3. Now, the big three solutions used are sodium citrate, sodium borohydrate, or acetocarbrate. Now, these aren't the only solutions that are used, but they're just the more common and more widely used. And each one has a different effect on this. Each one will make a different type of silver nanoparticles. It'll still be a majority of silver nanoparticles made. It's just they'll have different physical properties. For example, if sodium borohydrate is used, it'll make lots and lots of tiny grains, and tiny being 90 to 100 nanometers. And it'll make lots of these, but it's not very good at making the larger grains, the 100 to 250 nanometer range. So it kind of just depends on the specific application that you will need and what you want, like what you want desired from your nanoparticles and what they're going to be doing. So if you want a larger grain instead, you can use sodium citrate, and this will create the larger grains that are needed and more desired, but it takes a longer time to do so, so you just have to factor in your time constraints and exactly how big you need your grains, because it's an exponential graph and it takes longer for the slightly bigger grains. So it just depends on that, and that has a great effect on the structure of it.
Next, I will be talking about the properties of silver nanoparticles. Electrospun AgNO3 has many properties that make it an ideal catalyst. AgNO3 fibers excel due to the ease of manipulating the size and density of the fibers, allowing adjustment for use as a catalyst in multiple chemical reactions. Again, just as Nick discussed the different ways that you can alter the size and density of these fibers, this is incredibly important for fibers that you're desiring to use as a catalyst. Also, due to silver's property that allows it to be completely synthesized, its use as a catalyst will allow for a new set of chemical reactions, specifically those involving biologically important natural products. So the idea is, because silver can be completely synthesized, This may open up the range of chemical reactions that we're actually able to carry out, even chemical reactions that have not yet been discovered. Furthermore, silver's catalytic properties are quantity dependent. The better catalyst is required, simply electrospin a higher density fiber. This means that if you want a catalyst to have a longer duration, maybe for that particular chemical reaction, you just need a higher density fiber. Now, again, a catalyst can be something that speeds up a chemical reaction or something that slows down a chemical reaction. Or it can just be the fact that it allows a certain effect to happen during a chemical reaction. And again, being able to change the density of these fibers to make those changes makes it highly important for a catalyst. The main advantageous property is the material's resistance to harsh conditions, specifically high temperatures and solvents that would otherwise degrade other electrospun fibers during a chemical reaction. Also, one very important property that makes silver nanoparticle electrospun fibers different from other such fibers is its ability to resist deactivation and poisoning during a chemical reaction. Deactivation in a chemical reaction is when the catalyst stops working suddenly. This is obviously not very helpful when carrying out chemical reactions, because if the catalyst just all of a sudden stops during the chemical reaction, then the chemical reaction can't be carried out completely. Also, poisoning is another thing that happens to many catalysts. Poisoning is when the catalyst breaks down and contaminates the chemical reaction that you're trying to catalyze. The idea is that you can catalyze a chemical reaction from start to finish and then remove that catalyst and have just what you desired to have from the chemical reaction. Now, AgNO3, specifically electrospun fibers, greatly excel at doing just that, where many other chemicals and electrospun fibers fail. Because electrospun silver nanoparticles do not degrade and they don't poison the solution, they have the ability to be reused. Being able to reuse a catalyst has obvious advantages when carrying out chemical reactions. This saves time and resources and allows for more experimentation. So again, AgNO3 has ideal properties for a catalyst: its resistance to extreme conditions, ability to be easily manipulated and used as a platform for undiscovered chemical reactions, and finally its ability to be reused, are all very useful properties that set AgNO3 fibers apart as an electrospun fiber catalyst. Finally, we have Joe Hlebosky talking about the processing of silver electrospun fibers.
Everyone, my name is Joe Hlebosky, and I'll be talking a little bit about electrospinning and catalysts. First thing to know about electrospinning and catalysts is they require high voltage to extrude the nanotube particles. For this project, we chose silver nanotube particles because due to their high surface area and accessibility. First thing to know about processing and electrospinning silver nanotube particles is it's done using high voltage, and the droplets are literally stretched using electrostatic forces to extrude the tubes. Processing of silver nanotube particles is usually done using a silica and NO3 mixture. The mixture is bombarded with high voltage to produce the nanotube particles. The catalytic applications of silver nanotube fibers is used in the catalytic processes of blue dye, and which is used in hospitals, and these catalytic properties are good because they show up under UV light. In conclusion, silver nanotube fibers have a variety of catalytic uses in dyes and enzymes. Silver nanotube fibers are produced using high voltage and usually through a solution or pipetted. Silver fibers are usually doped with another material such as silica and NO3. The silver nanotube particles act like a catalyst due to their high surface area and low volume ratio.
In closing, electrospun fibers, specifically silver nitrate fibers, has many distinct advantages over other fibers. Its structure can be very diverse, ranging from 90 to 250 nanometers, has excellent catalytic properties, including the ability to be completely synthesized, its resistance to harsh environments, and its ability to be reused. And finally, the processing of electrospun fibers, specifically silver fibers, is relatively straightforward, as the silver only needs to be doped with silica and the NO3. Clearly, this material as a catalyst has many pros and few if any cons. Furthermore, there really is no alternative material to recommend, as silver electrospun fibers have taken the forefront of electrospun fiber catalytic applications. Thank you.